Looking at section 10.3 and talking about operations of radical expressions. Particularly, we're going to be looking at addition, subtraction of radical expressions. We're also going to multiply them. For our summary here, our operations with radical expressions include addition, subtraction, multiplication, as we just mentioned. In order to add or subtract, we have to have like radicals. You can see that here. Like radicals means it's the same radicand. The radicand, as we said before, is the piece inside the radical. The radical has to be the same as well, but since we're only dealing with square roots, not cube roots and fourth roots and so on, then all of ours are definitely going to be square roots and we're going to have the same radical part. But the radicand, the part on the inside, have to be the same. If they are the same as they are here, then you can add and subtract, and you keep the radical and the radicand, and you work with the numerators. 4 plus 6, the outside parts, is 10. If you got 4 square roots of 3 and somebody comes and gives you 6 more, now you have 10 of those. Similarly with subtraction, if you have like radicals as we do here, you keep that radical, square root of 5, and you have 12 minus 8 is 4. Now multiplication, you do not have to have like radicals. It says that very clearly here. You do not have to have like radicals. But when we multiply, what we have to be careful about is multiplying the outside parts, 3 and the 5, and multiplying the inside parts, the 2 and the 7. And that's how that's going to work. So, this is add and subtract. Well, these do happen to have like radicals. They're all square roots of 5. The radicands are all 5. So, all we have to do is keep that square root of 5 and work with the outside parts. 6 plus 2 is 8, minus 5 is 3. And we're done. That's it. That's the answer. As you look at this one, you should see that the square root of 2, 7 of them, but the square root of 2, this radical, is like this radical. But it's not like these two. But they are alike. So, thinking about order of operations and those kinds of things, let's work with the pieces that are alike in our addition and subtraction. So what is 7 times the square root of 2 minus 6 times the square root of 2? Well, we keep the radical. Those are like radicals. Keep the radical. And what is 7? Subtract 6, 1. So I'm just going to leave it written the way I already have it written. Next, I notice these two are like radicals. They both have the square root of 11. So it's going to be the square root of 11. Then I'm going to work with the outside parts. Those are really coefficients, but I like to call them inside and outside just for immediate clarity. So that's 8 minus 4, which is a positive or plus 4. And since these are not like radicals, we are done. So I'll move a little quicker now. Just wanted to lay a good foundation for you. These are like radicals. They all have the square root of 14, or square root of 13. And then the 3 plus the 4 is 7, minus 2 is 5, making the correct answer D. These are not all like radicals. They are not. But we'll put together the ones that are. And I hope you see that those are and that those two are like radicals. So we'll put together, like I said, the ones that are like. So for the square root of 2, here and here, we keep the square root of 2 and we work with the coefficients, the outside part. 4 plus 2 is 6. For these two like radicals, they both have the square root of 3. So we'll keep the square root of 3, and we'll work with the 8 minus 5. 8 minus 5 is 3. What kind of 3? A plus 3, or positive 3. Making the correct answer B. Now, I put this be careful here. I probably did that for a reason. Because this is a step, and this is what we keep doing, and it's taking steps. These are not like radicals, none of them. So your first impulse might be, hey, we can't do this. These are not like radicals. And as written, you're correct. That's why it says unlike radicands here. But a few days ago, we talked about the square root of 27. I see a square hiding in there. His name is 9. I see a square hiding in there. His name is 4. And in there. And his name is 25. Now, you may not be quite as capable of seeing those things immediately like I am. Of course, I've just had a few years of experience. But after you spend a little bit of time looking, you should be able to see all of those squares hiding in there. So you can see the 9, the 4, and the 25. So that's drawing off the previous work that we did in the earlier section, showing us how to do that. So, that being done, this square root of 9 is 3. Bring it out with the 6, you get 18, because it's multiplication here. We're left with the square root of 3. The square root of 4 is 2. Put it with the 8, you get 16, because it's multiplication. We're left with the square root of 3. The square root of 25 is 5. Put it with the 2, makes 10, because it's multiplication. We're left with the square root of 3. And so we at least would need to do that in looking at simplifying rational expressions. In our case, though, something quite interesting happened because we ended up with all like radicals. They all have the square root of 3. So I keep the like radical, square root of 3, and I work with the coefficients, or the outside pieces. 18 plus 16 is 34, plus 10 is 44. That's pretty good. 44 times the square root of 3. So here, the numbers are not as easy to see. The square hiding in there, they're not as easy to see probably as they were in the previous problem. It's probably a lot easier to see the 9, the 4, and the 25 there. So you have to do a little hunting, little looking in these to see if you can find them. Let me look at this first one. And let me remind you, I'm just going to come over here on the side. We could take the 245. This is what we did the other day. And we looked at 1 and 245. 2 does not work. 3 does not work, believe it or not. 4 does not work. 5 does. And 5 goes into that, I believe, 49 times. Now, we could go on down through here because there's others like 14 and so on. But I don't believe you can beat that 49 for a perfect square as far as largeness. So 49 times 5. But you can look. And it's okay to look. It's okay to be sure. With this one, I believe the square in there is 25. Because 125 is 25 times 5. I believe the square in that one is 16. Because 16 times 5 is 80. So we found the squares. Let me mark those as we previously have. So that was a square hiding in there. That was a square hiding in there. That was a square hiding in there. Now I need to clean it up. So the square root of 49 is 7. Put it with the 6, you get 42 times the square root of 5. Square root of 25 is 5. Put it in 3, you get 15 times the square root of 5. Square root of 16 is 4. There's a 1 out here. That's all. 1 times 4. And then I have all these like radicals. Square root of 5, square root of 5, square root of 5. And so 40. So I'm going to keep the square root of 5 so you can see how that has a great promise. So you see that the 42 plus 15 is 57, 61. Got it. Okay. So in multiplying now, that was addition and subtraction. In multiplying, remember, we do not have to have like radicands. We said that before. And here we do not have like, these numbers inside are not the same, and we can't make them the same. I mean, they're not the same. And so there's no square hiding in there. There's no square hiding in there. They're not the same. But they don't need to be the same. It's okay if they're not the same. But what we're going to do here is multiply outside pieces, coefficients, and then inside pieces, radicands. That's easy. We're not done, but that's easy. The reason why we're not done is because there's a square hiding in there. His name is 9. And you want to simplify this as much as possible. So the square root of 9 is 3. Put it with the 8. And the square root of 2 is the square root of 2. So the last one was kind of like a monomial times a monomial. And this is kind of like a monomial times a binomial. So we got to distribute here. Outside pieces, inside pieces. And distribute here. Outside pieces, wait a minute. The 4 times the 3 is 12. Okay, so now the 4 times the 2, that's the 8. And then the inside pieces, 2 times the 6. And both of those will simplify because in this case, the square root of 4 is 2. Put it with the 12, get 24. Did you notice, though, that that's done? There's nothing left inside when you take the square root of 4. So that's done. Now this, I'll need to rewrite because 12 is 4 times 3. 4 is the square hiding in there. And if I take the 4 out, the square root of 4 is 2. Put it with the 8, multiplication, with the 3 left. Now, they did a lot of work right here. I'd advise you not to pay much attention to it. Just notice that we have the same answer. So now we're just practicing, and we multiply the outside pieces and the inside pieces. That's the coefficients and the radicands, to be technical. Outside, 15. Inside, 24. And since 24 has a square hiding in it, which really the 8 did, I just chose not to deal with it in the beginning. And so the square root of 4 here is 2, makes that 30, and have the square root of 6, making the answer C. And that's kind of how these work. I mean, that's what we're doing here. Here's one where you can distribute and multiply here and here. The first one is 8 and 12. The second one is 10 and 4. Multiplying the coefficients, outside pieces, and the radicands, inside pieces, that's what I get. Now, both of those can be simplified. The first one has a 4, a square hiding in there. The second one, I should have just made that 2, made it 20, but I'll get there. That's 20 now. And this one, the square root of 4 is 2, makes that 16. And we're left with the square root of 3. And the answer is B. One last problem to do here, and it's just an application, an attempt to apply this material. It says find the area of a rectangle in simplest form with a width of that and a length of that. Well, I remind you that area is length times width. So if this is the W and this is the L, then we're going to plug those in. So I'll just write it. Area equal LW. Length, they say, is 5 times the square root of 3 plus 7 times the square root of 5. And width is 4 times the square root of 6 minus 2 times the square root of 10. Okay? That's strictly applying those two measurements to the formula because they've asked us here to find the area of the rectangle. And we know this formula to be the formula for the area of the rectangle. So I've borrowed that information, brought it over here so that we can work with it. This looks like, to me, the product of two binomials, which would indicate a real good opportunity to use FOIL. First, outside pieces, inside pieces. Outer, outside pieces, inside pieces. Inner, outside pieces, inside pieces. Last, outside pieces, inside pieces. Now, presuming I made no mistakes in that step, I do see the two middle ones are like radicals. They don't have to be just because of the O and the I, but in this case, they appear to be like radicals. I notice that the 18 has a square hiding in it, and so does the 50. I'm going to go ahead and put these two fellas together because they're like radicals. And so it's the square root of 30. And since we had a negative 10 and a positive 28, I think that's a positive 18. Now, I also have you notice there's no square in 30. There just isn't. There just isn't. So we found the ones that did have squares hiding in them. This one didn't. And so this would be square root of 9, which is 3, right? Square root of 9, which is 3. Makes this 60 times the square root of 2. And the square root of 25 is 5. Makes that a minus 70 times the square root of 2. And so that's this minus this. When I put these two like terms together, I get a negative 10. Let's see what they've got. That's what they've got. Same thing.